Okay, good afternoon, everyone, and welcome to this afternoon's PacTrans webinar titled The Modern Landscape of Traffic Signal Systems with Tom Stiles. My name is Cole Koch. I'm the Assistant Director of PacTrans. And before I introduce today's moderator, I just want to go over a few quick logistical things with Zoom in case this is your first time attending a Zoom webinar. If you move your cursor over your screen, you're going to see two icons at the bottom. One is the chat icon. You can send chats only to the panelists today. I would ask you to reserve the chat box for comments and technical issues you're having. We'll have people in the background here helping navigate technical issues. And then the other icon is the Q&A icon. So that's where we would ask you to do most of your interacting with today's speaker. Please feel free at any point throughout the presentation to leave questions in the Q&A box. You can also see other people's questions, and you can hit the thumbs up button and like them, and Zoom will auto sort those from the most liked to the least so that we know the questions that the most people are interested in hearing. I think that's it. So we'll get started. Okay, so today's moderator is Professor of Civil and Environmental Engineering here at the University of Washington. He is also the PacTrans Director, Professor Yin-Hai Wang. And I will turn it over to him and let him introduce today's speaker.
Thank you, Cole. Good afternoon, everybody. Welcome to the PacTrans webinar. Today, our speaker is Mr. Tom Stiles. Tom has over 15 years of experience in traffic engineering and operations. Using standard and innovative practices and his advanced knowledge of controller firmware functionality, he has optimized throughput and improved safety in hundreds of signal systems throughout the country. Tom has spent the past 10 years in various leader roles at Untitled, a traffic signal hardware and software manufacturer, designing traffic engineering aspects and the functionality of core products, and now works with an expert and innovative team guiding the group's overall vision. Currently, Tom is an Executive Vice President in Q-Free's ATMS division. This is previously Untitled Incorporation. Tom graduated with a BS in Civil Engineering from the University of Washington, and now lives in Seattle with his wife and two young sons. While spent summers cruising in the Puget Sound, he reminds his sons they can choose any school they want. The UW School of Civil Engineering, the UW School of Electrical Engineering, the UW School of Mechanical Engineering, etc. So obviously, Tom is a go purple, be gold guy. Tom, welcome to our PacTrans webinar. Now the floor is yours.
Thank you, Yin-Hai, for the introduction. Today I'm going to talk about a little bit of a high level of the modern landscape of traffic signal systems. And that'll include a bit of a history, talk about legacy equipment out there in the field and how that's kind of causing a slower transition to new technologies. And then also talk about some of the newer technologies being implemented now and in the future. So as Professor Wang mentioned, I am a diehard Husky fan. I attend a lot of games during the year, pretty upset about COVID this year. But in terms of being in the management team at Q-Free ATMS, I'm a lot more. So I'm a traffic operations engineer by trade, obviously went to UW. I have a strong passion for traffic signal control and systems, ITS development, working in the product manager role, being able to design those products hands-on, seeing how they work in the field. As of the last 9 years or so, I've really taken up a soapbox on open standards, and we've stepped that up the last couple of years with something called Free the MIBs. And the goal is to really, I'll talk a little bit about more, but kill the proprietary nature of the industry and make it more competitive so that we can see better innovation. And with that, just going out and preaching this sermon of open standards and innovation and change, the industry needs it, and you'll probably get a little bit of a piece of that knowledge today. Very quickly, because Q-Free does pay my bills, I want to mention we're a great company founded in 1984 in Norway, Q-Free purchased a company I previously worked at called Intellite, which was a leader in the traffic signal industry the last 10 years. Our global headquarters is in Carlsbad, California. We have a pretty big footprint worldwide, both in employees and in all kinds of different markets, reacting to all different sorts of different technology applications. And with that, the agenda today directly is we're going to talk about that progression in signal operations over the years, some congestions and roadblocks. I don't know if you guys notice, I have like a bit of a traffic signal theme here going in the agenda. I'm a nerd too, so if you didn't notice that, you'll find out soon enough. New technology in the fast lane. It's taking off quick, so fast that the industry is having a hard time keeping up with standardizing it. So there's some things we need to do as an industry to make sure that we can continue to develop these new technologies. And of course, the future traffic engineer. I'll get to that in a little bit of what, for the students out there, what you can expect in the future to be interacting with beyond maybe what you're learning in school. So let's talk a little bit about the history of traffic signals. Most of you have read things about this, different variations, but early 1900s, we were manually controlling signals. Police were using whistles, or they were manually controlling the actual signal heads. Our first interconnected system in 1920, you can call it a system because the concept was there, but essentially it was a half dozen signals all linked to a single button. So it was, from what I gather, a simultaneous green and a simultaneous red across those six signals. But it was a system in general, or by definition. There wasn't really any uniform traffic signal control manual or guidance until later in the 1900s, because people were out there inventing new ways to control traffic. Some had 2 indications, some had 3, some were just signs, various different measures. So the standardization didn't come till later. And then something notable in technology as well is the first actuation in 1930s, roughly 1930s. So the ability to detect a vehicle through electronic means. And I didn't really touch on safety improvements. There's a ton of huge safety improvements that have, made big differences in our industry, but today we're really focused on technology. So we get later in the 1900s, and now we're looking at solid state controllers. So 1940s, we had these electromechanical controllers with dials that clicked around. They were charged with 120 volts. The technician touched them wrong, they'd get shocked. So these solid state controllers were really the new era of electronics, and they were deployed out there in the field. Electronic detection started to take off. So with tube counts and pressure plates, or not tube counts, sorry, tubes and pressure plates. Tubes are still used today. You guys probably have seen pneumatic tubes stretched across the roadway counting cars, but we're not using them persistently in day-to-day traffic signal operations. The first urban traffic control system was deployed in the 70s, and it really just consisted of some signals out in the field. The system controlled time of day timing plans, and then also traffic responsive. So they didn't call it that back then, but essentially the system would read in some detection or occupancy inputs from the field, from the detectors of the controllers, and then it would push out the selected timing plan based on like some kind of defined algorithm of what those thresholds were. Pedestrian countdowns, I think, are more of a safety technology, but something unique. It was, to me, the turn of the industry that are kind of ancillary products to traffic signal control. The pedestrian head manufacturers and others and committees saying the traffic signal controller is not moving forward fast enough. We're going to start doing our own thing. And we'll talk more about that. And then, of course, modern day ITS. So although a lot of the technology deployed in the 90s is antiquated now, that was the turn of what we know of now of ITS devices in the field. So if you bear with me a little longer, let's talk about standards too. The 40s, we had the electromechanical controllers. Up until really mid-century, there was no standardization. It was kind of a proprietary custom thing. Every controller, the hardware was proprietary, how it operated the cabinet. The light's main purpose was to turn the signals green, yellow, red. Notice it's not red, yellow, green. You hear that a lot, so make sure you keep them straight. In the 70s, we had a standardization, NEMA TS1, and that was a huge deal because it did 2 things. It kind of governed similarities of operation of how the signal controller should operate in the field so that users are getting a consistent experience no matter where they are. The other thing it did is interoperability. So it governed the inputs and outputs, these 24-volt inputs and outputs, what each wire going in and out of the controller did. That means that theoretically, you could take any manufacturer that made a TS1 controller and put it in any TS1 standard cabinet, and you can intermix these things over time. Very basic standard, not a lot going on in terms of communications and things like that. Later in the 90s, TS2 came out. That was a big one too, because now we had some interoperability standards for protocols. The NTCIP framework tells systems how to talk to controllers. So theoretically now a manufacturer isn't, or I'd say an agency isn't tied to buying equipment and system software from the same manufacturer. We'll move along. I'll skip ahead to now where we have something called the ATC controller. The 2070 days back in the 90s was a big deal, microprocessors, so we could actually make software portable across different devices. But these ATC controllers are, you know, for the traffic signal industry, they're like a computer on steroids, right? So they're not as powerful as your cell phone on your desk right now. Hopefully you're not looking at it. But for the traffic industry, they're 10x more powerful. And the best thing is they allow us to expand our resources. And we'll talk about why that's important. So we have all this legacy technology in the field. Why can't the traffic signal industry innovate faster? Why aren't we building signal controllers the size of cell phones, things like that? Hopefully I can explain that a little bit. So this is 8 years old, the traffic signal report card. But back then, FHWA went out and said, let's find out the state of our infrastructure. Let's find out where we're at. And it was expected to come back quite low. So we got, you know, a D+ overall. Something really specific I want to point out is the traffic data monitoring and data collection. We got an F. And I'll explain why that is in a minute, but a lot of it's detection spread, right? So nowadays, big data, data analytics is all the buzz. That's all everybody talks about. That's what everybody wants. Yet just 8 years ago, our infrastructure got an F in data collection and monitoring. So keep that in mind. I wouldn't say we're significantly better now, although we've implemented a ton of new technologies in the field, but they're still not widely deployed. And when this report card went out, the goal was to show everyone what we needed to improve our infrastructure. Where are the gaps? Where are the holes? Why we need funding? It kind of turned on us. As a side note, the press and the public turned on us and said, well, you all must be really dumb engineers if you have a D+ in our infrastructure, right? You don't know what you're doing. So we're trying to change that, I guess you could say, impression over the years through public outreach. Most agencies now have PIOs, things like that. But anyhow, we still don't have that funding. So that's why the picture isn't significantly better nowadays, because there's limited funding to do these complete upgrades to get us out of this antiquated technology. Another big problem is proprietary lock-in. So I mentioned earlier that manufacturers, you know, we all follow a standard now, right? But that standard still gives people the ability to lock in the device and the system together in an agency. And we'll talk a little more about that. And then, of course, more recently, new problems we've never seen before is the pandemic. Budget planning, you guys know a lot of stuff's funded by gas taxes. Not a lot of people are driving right now. So it'll be really interesting to see where funding comes from in the future and how we can improve our infrastructure with that reduction. In the past, and even up till now in a lot of areas, siloed solutions are deployed. And what I mean by that is, I'll get in a little more detail, but different market segments, different manufacturers, nobody really, we talk to each other, but it's very cumbersome, very difficult. Inferior security. So if you look at the traffic signal infrastructure compared to even how you interact with your bank or you sign into your computer, the security is well behind the curve. So a lot of cabinets, you know, are accessible by a number 2 key. So anybody with that key available on eBay can open it. I'm not telling you trade secrets. This is pretty much public information. Legacy equipment, we talked about a little bit, but you can't do stuff that you need to do for connected vehicles, for data collection, even for enhanced operations scenarios with this limited equipment in the field that's 20 years old. And communications. So when we talk about anything about data analysis, connected vehicles, even improving operations with traffic responsive or adaptive algorithms, we have to have good communications. So that brings us into just a little more detail about the silos. What does that mean? Well, right now, when you go out in the industry, for the most part, to have expert systems or really good systems, you're looking at a separate system for freeway management, a separate system for traffic signals. Freight or port authorities or private fleets might have their own system they're using to manage their freight. And detection, of course, I'll talk a little more about this in a minute, but they've moved on from traffic signal controllers and they're doing their own things now, right? Because signal controllers are moving too slowly in innovation of hardware. So when you have all these things segmented out, one, it makes data sharing very cumbersome, right? So there's some protocols and standards out there to do so, but it's a custom implementation every time you interact with someone new. Another problem is if you have these separate systems, you're not truly always working together, right? Like a freeway management group and a traffic signal management group, they might talk, they might have similar objectives, right? But they still have two separate systems. So at the end of the day, even though they're coordinating together, they're still operating in a completely separate fashion. And that's overlapping investment, both in technology, because you're buying product solutions that are completely separate that might have overlap in terms of functionality, and your staff's overlapping. You have, instead of having two people to run two different systems, maybe one person manages that system while the other person is out there improving operations enhancements or trying to manage congestion or an incident. So we can do more with our resources if we can start to combine these things into one. Security. I talked about physical access, this number 2 cabinet key. Cabinets are easily opened. In Seattle and Portland, you know, we have a lot of problems where people are using cabinets for storage out there in the field. They're running fires in them. They're plugging electricity in to charge their devices. So it's a big problem getting access or having people breaking into cabinets and gaining access. Once they're in there, the controllers and other devices don't necessarily have up-to-date security protocols, right? Most controllers until a few years ago only had a 4-digit code in them. And that 4-digit code was the same for everybody. It was a single 4-digit code that restricted read-write access. So you can only imagine if an agency's 4-digit code gets out, it doesn't matter anymore, right? So most people didn't even implement them. And a lack of knowledge and training. I think as a traffic engineer, the last thing at least I would have thought about throughout my career working consulting and field operations was the security of the equipment. I didn't really think about that. I was more focused on how it's operating in the street, how it's turning the lights, how it's serving transit priority for light rail, things like that. So these things come into a bigger problem than just physical access and harm. It becomes a cybersecurity issue, right? A lot of times traffic signal connection or systems are monitored or managed on a city network. So now all of a sudden, if there's equipment in the traffic signal side or software that's vulnerable to cyber attack, you've opened up the entire enterprise, the entire agency's piece. It's a loophole possibly. So there's some concerns there, and also safety. If we add a bunch of new functionality that does some new really great, crazy things that are safe and improve operations, as long as they're used properly, you don't want people getting in there maliciously, right? Because that could cause a safety problem. Talking about equipment specifically in the field, specifically signal controllers and detection. Signal controllers, they're really lacking, the older ones are lacking the technology to process tons of data. There are also, a lot of them lack resources. So an older controller that were being sold up to 3 or 4 years ago might have had limited time on the processor, limited memory available to the software that would operate the signal. So if a customer or maybe a vendor or whoever wants to add some cool new coordination feature to reduce transition time, there's a possibility you'd have to steal from other functionalities. So maybe for that build of software, that had half the detectors the previous build had, because all those resources used up by half the detectors in the software are now being reappropriated to a coordination thing. So these ATC controllers give us the power to add new stuff without taking away. Also, proprietary protocols are killing us. It really shuts down interoperability. It shuts down competition. And that's why until just recently, innovation was very slow, because when you're selling into a market and you don't have to do much to be competitive, why would you invest a ton of money in R&D and things like that? And of course, end of life. I can't tell you how many controllers are out there in the field that are 20 plus years old. And I don't know if that surprises people or not, but again, there's no funding that's really earmarked directly just to upgrade a signal controller. It has to be through safety funding. It needs to be through environmental impact funding, things like that. So there's projects you can do it, but to some large cities, that funding is very hard to get or not available. So we have a lot of equipment out there that is operating 10 plus years past end of life. And it's really not fit for today's modern kind of operations strategies. Detection, legacy detection doesn't have trajectory data. It's a simple on-off. Is a car on the loop? Is it in the zone, or is it gone? And so modern detection is pretty cool. It's actually has the ability to track pedestrians, cars. So now not only do we know is the car there or not, we can see where the car is going potentially, or where it's been, because we're tracking it. We can also find out how fast it's going or how fast it's decelerating. So there's a lot of really cool safety applications and operation scenarios you can implement with that kind of knowledge. And then of course, as we get into big data, I'll talk about that in a minute. Our best eyes in the street right now is detection. And so to improve that vision, we need more detection. More detection costs money. We're back to a funding issue, right? And of course, this slows innovation because, one, if there's not equipment in the field to run these really cool, innovative software products, then it's not going to be implemented as quickly. Also, we talked about a lack of funding, and it blocks new players. So it's very difficult to have new technologies in the traffic signal industry because we still have to support all the legacy stuff. We devote a lot of our resources to supporting legacy solutions with brand new software technologies, because if you don't, you can't cover the market. So imagine if we had all new equipment out there in the field that was very modern, dynamic. It would open up other players to come in and introduce some new cool technologies, and it would also free up our R&D as an industry to go chase brand new cool stuff. Communications is the last one we'll talk about in detail here, and then we'll get into maybe some more fun stuff. But essentially, comm is critical, and IP-based networks with Ethernet started being installed 15, 20 years ago. But the issue with that is a lot of those early systems are old. Also, fiber gets cut by contractors, or if you're doing Ethernet over old serial copper lines, they degrade. Wireless radios get bumped by wind and branches falling. And soon enough, a lot of agencies, especially smaller ones that can barely afford maintenance and things like that, or have to appropriate their funding all to maintenance and roads, their communication's no good. So now we have this great signal system installed, these new controllers out in the field, and you can't actually talk to them. So we're not really gaining the value we need out of that solution. Serial deployment still exists. Cities of 1,300, 2,500 intersections are out there, and 90% of the city is still operating in serial. Some of them converted to serial over Ethernet, so they're at least bringing it back over IP, but their equipment is still communicating in a serial fashion, which makes it kind of slow and limited to what it can do. Lack of training and knowledge, again, this isn't meant, when I say that's not an insult, it's more as us as an industry. We talk a lot about raising the ceiling, like how do we get to the next greatest, biggest thing, which is kind of the whole next section. But before we get there, you know, Rick Denny from FHWA made a great point. We also need to raise the floor, right? We need to bring everybody who isn't even to the current level of technology. We got to figure out how do we educate it? How do we find funding for them? How do we get the industry up to a point that's acceptable? Remember that report card? We got to get out of the D+, right? The D+ isn't because somebody's doing a bad job. It's because we as an industry, and we, I want to say, like in terms of funding our infrastructure, we're failing that. And then the legacy industry standards bullet is really kind of noted there because it's very difficult to implement the protocols as they are standardized now. We need more modern protocols that can be integrated much faster. When you're integrating, let's say you sell a traffic signal system and you have 3 different manufacturers' devices you want to integrate. It's really a cumbersome process right now, and it's kind of a one-off implementation of each. And there's really no reason with modern web technologies and protocols, JSON, things like that, that we can't make this more dynamic and much faster to implement. And then I kind of talked about already the reasons these slow innovation. Again, cost is an issue, but also just communications, being able to share the data, being able to get the data from the site into the system. So not all is lost. All the doom and gloom, maybe you see that as, it's more of a discussion of where legacy technologies hold us back, but we're also doing some really awesome things. And if you look at the industry now, it's connected. Mobility is connected beyond traffic signal solutions, beyond ITS, Uber, you know, all these different new technologies, even in rideshare programs. I can rent a scooter through my cell phone. My kid loves that. We cruise around the neighborhood here in South Seattle. But the real issue is it's here. We're not looking into the future anymore. We talk about big data. When we talk about innovations of operations, the way we even interact with our system. So when I say innovation operations, I'm not talking about the equipment. I'm talking about even the processes and the way we manage our infrastructure. It's here now, it's changing, and it's changing extremely fast, faster than the standards can keep up with. So let's first talk about data. Everybody's talking about data, not the sentient being from Star Trek, if you're a Next Generation fan, but data, big data everywhere. And there's some, I'd say the IT industry, there's a lot of startups that are coming into traffic as well. There's a lot of big names out there just in IT and different social apps, things like that, to where the appearance in the world and the greater world is that it's not necessarily about the quality of data, it's the quantity. And the more data you can get, the more valuable it is, because then you can start to create all these different scenarios and ideas, right? So this is from 2018. So these numbers are probably significantly higher now. But in 2018, we were collecting as a global entity 2.5 quintillion bytes of data a day. And I think that's somewhere around 2.5 million, maybe it's 25 million. I'm not doing my math right. But anyway, terabytes. So that's quintillion, 2.5 quintillion daily, just in one day. 90% of that back in 2018 was generated in the past 2 years. So 2016 to 2018. So 90% of the world's data was generated in only 2 years. And I bet we're screaming past those marks right now. It just uncontrolled, or maybe you call it controlled chaos. So in traffic, we're more about quality of data than quantity, thankfully. But it's definitely changing the way we do business. And not because we have to, that's part of it, because the world's going to data-driven concepts, but it's more valuable. It allows us to do more with limited resources and limited opportunities. So with that, though, when we have all this data and traffic, we're not collecting 2.5 quintillion bytes of data daily, but we do the stuff we collect. We need new formats and ways to handle this data. We can't just plug it all in the SQL Server and manage it daily. If you do a query on terabytes and terabytes of data in SQL Server, you're going to be waiting minutes to get that query, right? We need relational databases, or sorry, time series databases that are super fast in hosting. Also, we need scalable technologies running our systems, maybe some edge computing like factored in there, right? So you need a system that's sized to collect and monitor and manage during rush hour traffic, but it doesn't need to be doing that 24 hours a day. So why pay for all that extra resources? Why pay for these giant servers when you're only using them for a few hours a day at that capacity? And then of course, new operations practices. I mentioned it's changing the way we look at how we optimize and manage traffic. So the biggest change when it comes to data initially in the traffic industry is something called high resolution data. It was created about 15 years ago, maybe 12 years ago, but it really didn't hit mainstream and become popular till a few years ago. And what high resolution data is, there's a big difference between how we've done things in the past. In the past, a traffic signal system would hit a controller once per second and say, what are you doing? What are you doing? What are you doing? Right? Every second. And the controller would reply with whatever the system was asking for. The problem with that is, let's say my communications goes down for a couple hours. I don't know, there's a thunderstorm and some branches are waving from the radio, or maybe cell service dropped out. That data is gone. I'll never see it again, right? The system couldn't collect it, so I'll never see it. Also, the system's only seeing what's happening on a per second basis, which means the resolution of that data isn't quite as good. So this high resolution data format, there's two major factors that are different than how we used to do it. The first is we collect it locally on the controller or the device. So every 1/10 of a second, that's the second piece, 1/10 second resolution, we're collecting a huge subset of data. I think it's around 200 indices now, maybe 250, depending on the vendor. But we're storing that data up to a day's worth on the controller in near real time. And then whether it's every 5 seconds, every 15 minutes, whenever you want, that system pulls that data off the controller and stores it up and stitches it into the rest of the data at the system level. So if I lose communication now, I'm okay. I still have that data stored locally in the controller. The system reconnects, stitches that data into where it was missing. There's some other cool things we can do with it on the controller too, I'll talk about in a bit. With that though, so we're not collecting trillions of terabytes, but we are collecting about 45 megabytes a day per controller. So for the traffic industry, this is a giant increase in data, more than we've ever managed before. That's like 16 terabytes a year for 1,000 signals. So I know it doesn't sound crazy. I mean, I think I have maybe a 10 terabyte hard drive that cost me $100 sitting on my desk, but 16 terabytes a year for traffic signal data is a lot of data just for signal operations. And that includes all kinds of things. I mentioned there's 200 something indices right now, but it's like a 10th second timestamp of when it goes green, yellow, red, transition times, preemption, transit priority. When a PED push button's pushed in, you could have it configured to the cabinets opened or closed. So anyway, a lot of information. It's very powerful. So some of the things we do with this information is something called ATSPMs. And the ATSPM started, I think I mentioned Indiana about 12 years ago, started this high resolution data piece with ATSPMs, automated traffic signal performance measures. And the goal was to use data to tune your signal system, but not like a synchro model, right? When you build a traffic model, you're looking at counts that you collect on a Tuesday through Thursday. A month later, you get your model built, you plug the counts in, and then you use some kind of like black box algorithm that generates traffic to determine how's my level of service? Is it going up, down? How am I improving? ATSPMs enables a traffic engineer to look at real data in a graphical format and determine, are my platoons going down the corridor tight enough, right? Am I getting my progression okay? Are all the movements of the signal well balanced with occupancy? So there's a lot of really great information that we can engineer and optimize our system and network or make safety improvements based on actual post-process data, not some kind of a algorithm or modeling program. But We can also do really cool real-time stuff with that data. So all that 10-second resolution data, it's available on the controller up to a day, right? So we can start to put analytics on the controller itself. So if I'm an engineer or technician in the field and I want to see, the occupancy of my different approaches for my split balancing, I can view those charts in real time in the controller or through maybe my cell phone on a browser or a tablet or my laptop, and just log into the web browser of that controller, just like you would when you will log into your Wi-Fi router at home, right? And start to configure and monitor all these analytics. Another cool thing is we can drive adaptive algorithms with it. So when you're running distributed computing in the edge, these controllers can work together in a network. And those same theories that you use as a traffic engineer, when you look at those charts to say, are my platoons tight enough? You can develop an algorithm with that using some fancy math. That's why we have mathematicians on staff to actually optimize the timings based on that same input data. So this is just an example, I think, of really specific data or data that's specific to the traffic signal industry with no outside kind of interference that we're collecting and managing on our own. Detection. What makes ATSPM so powerful? Well, that high-res data and any data we get for a traffic signal has to be driven by some kind of inputs. Detection is a great one. So if we can't see it, we don't know it exists. There's many types out there. The modern day detection I mentioned or alluded to earlier, we can often get trajectories out of those. So not only can we see is the vehicle there or not, we can determine where it's going, or at least make a good educated guess. Also, some detection manufacturers are implementing machine learning algorithms. So you talk about video detection. Some of the problems in the past with video have been, I have a black car at night and it's in a shadow, and so I can't see it. The video doesn't know what it is. So what we would do as an industry is that vendor would go back to its developers and say, the camera's not seeing black cars in shadows. So the developers would tweak that algorithm to find out the most probable return there's a car there if it sees a black shadow or a black car in a shadow. But then that has to be pushed out to an update. All the other stuff in the field has to be updated. Nowadays, there's at least one I know of detection manufacturer that a technician can stand by and say, hey, you can't see it, camera, but there's a car there, and push a button. And now essentially that has learned that that's what it looks like, and it automatically integrates it into the algorithm and distributes it out to all the detection equipment in the field. So there's a lot more modern detection out there to see what's going on. Probe data is a new hot topic that is very valuable long-term. Probe data is taking maybe connected vehicle data, but also if you think about cell phones, cars, they all have cellular connections, they have global positioning. We can start to tap into this data and get at least a sample of what the cars in the field are doing. So even if I get 20% of the cars in the platoon rolling down a corridor through probe detection, that might be enough to optimize signal timings without having traditional detection sitting in the street. Because we talked about it before, to get better visibility a traditional way, we have to increase physical devices in the field. Well, with probe data coming into kind of a play, that's not as important anymore. So we're not quite there, but that transition is happening. And with connected vehicles, the ability to see either remotely through the cloud or see them in real time from like a vehicle to field device connection. So what are we going to do with this data in terms of operations? I talked about how we can manage it to optimize signal timings, to identify safety issues. I just kind of threw a couple examples out there that I've actually seen used in the industry in reality. Like, for example, blending this data from a traffic accident database from the State Patrol. An engineer could look at it and say, how many right angle accidents occurred at intersections where FYA was deployed? Or maybe how many occurred at intersections with a flashing green, or I'm sorry, a permissive green, I'm thinking Canada, but a permissive green versus an FYA. And now we can start to identify what sites need to be upgraded to FYA to reduce crashes, right? Also, like, how often is a pedestrian call resulting in transition? We can get that direct answer straight from the high resolution data. But I think what's even more rad is we could tap into some of these video manufacturers' data where they're tracking pedestrians via video. And then we could start to say how many pedestrians were standing on the corner when transitions caused. And if I find that I've got a ton of pedestrian loading at that intersection every time, maybe it's time to revisit my traffic signal timings, optimize them so I'm not throwing myself out of chord every time I have a ped movement, right? Impact of TSP operations. This is valuable for two reasons. The metro or the transportation agency loves to know how much time you're giving them, but also it's great as a traffic signal engineer to know how much is this affecting me. So if we implement TSP to get buses moved through a corridor faster, then how much time are they stealing from vehicles? Are they actually causing delay on passenger vehicles? How long is the bus being delayed, right? So there's all this different rich data we can analyze later. Is my chord plan still working? Really falls back to ATSPMs being able to tell you, you know, is traffic behavior changing to the point that it's time to go out and re-engineer timings or possibly implement some newer technologies like adaptive or traffic responsive? Did a driver run a red light? This is, I think, a really interesting implementation of the high resolution data. So in Utah, they were able, the traffic engineers there, working with the state patrol and getting like timestamps from seeing a vehicle, I think, struck a motorcyclist at an intersection. And the vehicle said that he had a green light. The motorcyclist said it was green his direction. So they were able to track the vehicle via video and then find out, just because the traffic loading was low, when he hit the advanced loop at the intersection. And through this high-res data in court, they reconstructed the signal operation during the crash and proved that the driver did have a red light and he ran it. So maybe you don't want to get in that kind of litigation as a traffic engineer, but that's just the power of that data is available. Some agencies choose to delete it immediately so they don't have to think about that after they're analyzing it. They don't want it to be a legal issue. Other agencies like Utah, they see the power in that and sharing that data. And then a couple other examples here too that we can cover in questions if you guys are all curious. So what is data's real role? We talked about some ideas, but we're just beginning. I mean, there's a cliche that Curtis McBride from BioVision likes to share a lot. And it's with all this information, we might find out that 1 + 1 = 3, right? Meaning we may not really understand what we're capable of until we start to get this data and these solutions and these systems combined and all these operation scenarios start to sprout up with new ideas. So data in general, what's being implemented now is trend analysis. So the ability to really monitor if a detector is bad or not. So instead of saying, if you know that every day that detector at 5 o'clock is supposed to be detecting 30 vehicles, and then one day it detects 700 or 800, something's wrong or traffic's really screwed up there. So it gives you a little alert, right? Also, trends can help track problems. So if you see in the trend or the system's analyzing in a trend analysis that the traffic congestion is slowly getting worse, then slowly gets better, it's probably just a peak hour issue. But if it finds during that trend that traffic just jumps up and is extremely congested all of a sudden, then you might have a form of automated incident detection to tell you something's wrong. With all that data too, and all these different technologies, we can build in machine learning, automation. So if a traffic technician or engineer corrects a problem or manages an incident, the system's actually recording all that and essentially learning that behavior, right? And with that too, it's learning behavior of traffic out in the field. So on the freeway, it could start to identify if the traffic congestion is matching a certain model that's resulted in an accident 4 out of 5 times, then it can predict it and say, look, we're approaching the same type of congestion model. We're probably going to have an accident. We need to do something to mitigate this problem. And then this is really kind of a funny dream thing, but it's been presented a lot as Siri, I guess, is the presented in the industry. But okay, Google, like the ability someday, this is not here yet, but to ask your system, where your hotspots are today, using these last 3 bullets of kind of management, like where are my hotspots today? How should I fix that? What do you recommend? So let's talk a little bit about connected vehicles because they're going to just add to this data pool substantially, probably more than the high-res data. But connected autonomous vehicles, the goal is, of course, to have a vehicle, a car, a bus, fleet, whatever, and also pedestrians, even though it's called connected vehicle, talking to the infrastructure and talking to each other, right? So being able to communicate to the infrastructure with safety messages that, hey, my tires just slipped on the ice, and then now that maybe the signal controller is the edge device in that case, and it all of a sudden takes that in and broadcasts to everybody, all these other cars, an ice warning on their heads up display, right? So there's a few different methods of connected vehicle. One is vehicle to vehicle, so vehicles talking to vehicles. Another is a vehicle to infrastructure, which is really like a DSRC-based radio, a special protocol where the vehicle is directly communicating over radio to the traffic signal or the street light or wherever this radio is located. And then V2X, which is appearing to be the technology evolving now or coming out in the lead. And V2X is vehicle to everything, right? So really 5G is what's driving that technology. These different connected vehicle messages can be safety messages, just an info message that maybe the freeway is closed ahead for an incident. It could be service requests from a fleet. So emergency vehicles could say, I need emergency service right now to get through this signal. The thing that is most important about this is connected vehicle scenarios can go up in the cloud through the system and then down through cellular to a car, or they can go, like we said, point to point from the vehicle to the infrastructure. And with that, what's that mean? The infrastructure needs upgrades. So not only do we have to have a traffic signal controller that can produce the correct data in the right format to be used out there, we also have to have a radio at the intersection. There has to be a radio in the car, and it all has to be in, really for safety, sub 250-second millisecond. For anything else, we need it within 500 milliseconds of latency. So some applications that have been done in pilot deployments or in theory is safety applications like a curve warning system. So there might be a radio in a curve, and as your vehicle approaches it, the vehicle tells the curve or the unit how fast it's going, and the curve says, hey, you're going way too fast, you need to slow down, right? I don't know if you guys, it's not connected vehicle, but the cars are already capable of this. My Outback, when I put it in, I wouldn't call it auto drive, it's not that by any means, but the eyesight cruise control, if I approach a curve too fast in cruise control, the car automatically starts slowing down. So it's almost doing it on its own, right? Imagine if we also had some feedback from the infrastructure that could tell the car if it's icy outside, and the last two cars slipped, and so you need to also slow down even further. Pro data detection also, so using this connected vehicle application to get data into the controller, into the system for analytics, for adaptive, for operations, all kinds of stuff, warnings. And then this vehicle-to-vehicle communication piece where vehicles are telling other vehicles, hey, I'm approaching the intersection adjacent to you and neither of us are stopping. Somebody needs to stop, right? Or maybe it's just telling the vehicle that it's raining, and so you need to turn on your windshield wipers. Commercial solutions that I'm seeing actively deployed, not as like a pilot kind of a demo, but as actual solutions, are travel information. So the ability to broadcast safety messages, construction zones, things like that. Often this is done through the cloud, right? You guys see it on your Google apps or your Apple Maps. That data that there's a construction zone is coming from some API. It's really, I consider it a connected vehicle application because the system somewhere is producing this information, it's spitting it up into the cloud, out to a API for Waze or Google or whoever, and it's feeding it back to you in your heads-up display in your car or on your cell phone. Emergency vehicles and private fleets can start to, because they can control the equipment installed in their vehicles, they're starting to install radios for direct vehicle to infrastructure communication that are requesting service. Maybe it's tracking them to know where they're at, right? So different ways to manage these things. Travel time prediction. This isn't travel time like how long is it taking me to get from one location to another. It's more how long until this light's going to turn green, right? So if you look at Audi, there's a company called Traffic Technology Services, and they push a lot of data, signal operations data, coming out of an agency system. They push that with an algorithm to Audi, and the Audi heads-up display, when you're driving it down the road, it tells you the approximate speed you should be driving, obviously based on probability, to get all the green lights in the corridor. So this is a couple things. One, it's less stressful because now you're not stopping at a bunch of red lights. It's better for the environment. And if I don't have to stop at a bunch of red lights, I'm probably going to reduce accidents too, right? Rear end accidents and things like that that are often caused by the stop and go of traffic. The other thing is vehicle efficiency. The auto manufacturer can start to use this data even with prediction to say, I just got to a signal that's red. I know it's probably going to turn green in 5 seconds, so I'm going to leave the car running. Or it might say, actually, it's going to be 30 seconds till green. I'm going to turn the engine off until 2 seconds before and then start it up automatically for you. And something I left out in the CV messaging is an actual map. So something really cool about CV standards is you can kind of see in the graphic here from a system, these orange lines are representing each lane of the intersection. It's geospatially located. And there's a standard message or a file that gets broadcasted from that intersection to any vehicles approaching the area. And it basically tells those vehicles what the intersection looks like, and then the vehicle can respond to them. And now the system can track what lane is that vehicle in and what's their current trajectory. So extremely powerful scenarios for safety and operations are evolving right now. There are problems. So DSRC is a technology that's been going for at least 10 years, maybe more, and fighting to get it deployed out there. But there was an issue recently, if you are or not aware, where DSRC in a 5.9 spectrum, the wireless spectrum that was dedicated for safety, was threatened. And 5G was threatening it for both private and public, I would say, uses. But the FCC has recently ruled that DSRC is no longer in that protected spectrum. So those radios will go away. Luckily, the industry in general has been preparing for it. Most vendors are looking at V2X, most radio manufacturers are V2X, but that leads us to some misinformation out there about V2X. And I don't know if it was because we were rallying for DSRC or what. I'm not particular to one or the other solution. Doesn't quite matter to me, but a lot of people would say for V2X is 5G. So does that mean that to get that safety, protection in a car, that a user has to pay a monthly cell phone bill to use that cellular service? And so the argument was that if you want that guy to get in his car that morning and he turns on the ignition, but he can't afford the cell phone bill, are we going to jeopardize his safety driving to work because he can't afford a bill? It's a huge misnomer. So V2X 5G actually includes a point-to-point protocol as well. And if you think about it, it's a really crappy analogy. And for experts, you'd probably chastise me for this. But think of the analogy of like serial versus IP communication. They're both transmitting data. They can both transmit the same data. It's just in a different format, right? Think of like V2X cellular, the same as DSRC. They're just transmitting it in a different way. There are 5G solutions with cellular towers, which are being commercialized and put out there, but it's not, you can also do this point-to-point piece with the radios. The problem, whether it's V2X or DSRC, is again, it's like the same song I keep singing, guys. It's unfunded, right? And so that's why we really need more engineers, more people, more agency staff, more technicians, whoever, people who know the industry to get involved in politics. Maybe not be a politician, but we have to be out there spreading the message, educating politicians, educating directors, of our groups, managers, cities, mayors, all this, that they need to take this message to Congress and say, if we want to improve safety, we need substantial funding to upgrade our infrastructure, right? Because we can't do this with 20-year-old controllers. Scalable technologies and edge computing are a reality now, but we can't afford to upgrade the infrastructure. So it's possible that we can do this edge computing or this distributed processing where, maybe all the controllers, the system lives on all those controllers, right, across the board. And so there's no single controller doing it. They're all thinking like a giant brain. That's really far out there, but maybe it's not that far out there in terms of the future. And of course, the OEMs, the manufacturers of the automobiles, they're moving fast because there's money involved for them. It's a feature in a car for radar, cruise control, being able to talk to cars, getting all that valuable data back for maintenance, things like that internally for them. They're kind of disconnected from what we do. The ideas that we talk about in terms of what you would think is really basic traffic operations, they don't understand, right? They've never thought about it. So we also have to work closely with them on committees, standardization, and educate them on what we do to ensure that what they're doing doesn't, cause safety concerns. Security is a necessity. So we talked about security being an issue. We need an end-to-end security solution. It's not acceptable for us as traffic signal people to say, you know what, our devices are going to hide behind a switch in a cabinet. We'll let the IT industry deal with that. Our software has got to be up to date. Our products have to be up to date. We have to implement security standards. For one, physical security wise, a lot of agencies, not a lot, some agencies, it's a small movement right now, are turning to smart locks, where they're actually digital keys for the cabinets. If you're at university, if you're in a private group, if you're in a city, for years, we've been using key cards to access buildings, right? Or labs and things like that. We've always had key cards. Your Husky ID gets you into certain labs that other people can't get into. So I just had to plug a Go Huskies somewhere in the presentation there. But anyhow, it's just now coming to be acceptable in the traffic signal industry to say we can use a digital key to open a cabinet. And with that, once you're in the cabinet, we have to have user accounts and devices. You got to lock that device per user so you know who's accessing it. You can control what they're accessing and when they're doing it. Network, same thing. Traffic signal engineer, I am definitely guilty of this. I did not learn a ton about IT in school beyond what I knew on my own, setting up, building computers and networks and things like that. But it was self-learned, a lot of it, some reading on Google or whatnot. But essentially, when we deploy all this comm equipment out there in the field, we're not always aware of how it should be implemented. So we've got to make sure that we're either employing the right people or at least getting the right recommendations, that that equipment that's out there has security set up. It's disabling things that shouldn't be, that aren't in use right now. It's restricting access to the network as a whole, not just a signal device, but the whole ecosystem, right? And for that also, we need to have the ability to transfer data securely. Most controller standards are not secure when you look at the industry standards. So we have to look at private ways of doing that, not proprietary, but maybe using more modern connections and protocols to transfer our data, like HTTPS, SCP, things like that. So new technologies for an old industry. These are technologies that are being leveraged now in traffic that have been around the IT world for a while. They're evolving more, but I think the public industry, you know, we were entered in a computing world with Windows. It was Microsoft Windows. So everything with an enterprise went to Microsoft Windows. Some people hooked up with Novell for a while, but eventually everybody's on Windows. So it's nothing wrong with that. It served our purpose for a long time. But Microsoft Windows, Microsoft SQL Server, these are not technologies that are really, at least they're working towards shifting, but they're currently not powerful for all this big data. They're not as scalable as necessary, right? We're still depending on other technologies to run those on to be who we are, or I'm sorry, to do what we need it to do. So there's a lot of technologies developed by major tech companies like Google, Intuit, Netflix, all these guys. You look at Netflix, they're managing millions of people streaming movies all day long, right? Especially right now with COVID. I've been binge watching Next Generation, Star Trek. I already alluded to that earlier, but somebody else is too, and my video is not skipping because of it. So there's a lot of technologies in terms of data management, user management and access, in terms of framework on how the operating systems run on hardware that we can leverage as a traffic signal industry to make it better. What are the benefits we gain from these new technologies, right? Why are we just going the next flashy thing? Can Windows do the job? Well, the reason we look at these new technologies is, like, for one, software as a service. You look at Microsoft Office 365, OneDrive, they're all available online. There's some hybrid things where you can have an app on your computer too, but this is software as a service is the future. It's now. Signal industry is moving slow, but it will move. It has to, because that's the way the world is moving. And so the ability to deploy your software in a SaaS environment, a software as a service, or a cloud environment, or in your back room. A cloud is just 3 or more computers. So there's really no reason we can't use those same cloud technologies, deploy them in the back room on a server, and then when the agency's ready, migrate that over to SaaS. The best part about these new scalable technologies is you can do that with the redundancy built in and these clusters, the way they're managed. You can do it without taking the system down. So you can install new software, you can shift where it lives in the cloud or in the back room, all with a live system without actually removing service. Databases, you know, Microsoft SQL Server is a relational database, really great at what it does, one of the leading technologies in relational databases. But when you look at huge data sets, it's slow. So if I want to see things in real time, if I want to have a slider on a map to look back in history and then back to where I am, maybe predict the future at some point, and watch my data map or my graphs and charts change dynamically, then I need to have something fast, a time series database, something that can host that information up immediately as fast as I can snap my fingers. APIs as well. So I talked about how integrating with other systems, other markets is very cumbersome, one-off solutions. We need better ways to manage data. You look at marketing, they're probably my marketing director's on the phone, or EVP, so I shouldn't say too much horrible things about marketing, but they, if you look at marketing in the world, it's about quantity, not necessarily quality. They start with quantity, then they find quality in that data. Well, they're really good at sharing data though, right? They have the ability to bring in data sets from all different kinds of formats, protocols, and things, and dump them into one big package or one box to pull from. And that's where we as an industry need to get better at working together to issue these modern protocols, to implement them. And I hope that standards committees will change the way we generate standards as well, so we can keep up with these changes. Otherwise, it turns into more one-off solutions. So we got to work together on that. And of course, a user interface. I think some people think a user interface is just a sexy, cool kind of part of a traffic signal system. Maybe you've never heard those words used in conjunction with a traffic signal system, but essentially, we shouldn't have to work in some kind of archaic DOS-like thing, right? Like, I should get the same experience from a traffic signal system that I get when I'm working in an app like my bank or something, or anything else. It's web-based. It works through my browser. It's intuitive. Like Google Maps, you're working within an app in the web browser, and there's no reason traffic signal systems or even a controller software can't be the same way. It allows us, using these modern technologies, to add features faster because the type and the way it's developed, components can be reused. And again, it provides an actual modern day experience with the signal system. Just to throw out, I talked about who generates these technologies and builds them, but some of the technologies being used in traffic now to make these scalable, robust platforms is like Linux, React user interface developed by Facebook, but just an incredible user framework or user interface framework that's reactive to your phone, your tablet, your laptop. It's very dynamic. Postgres is a open source relational database. There's also a time series one. I think it's called Influx is one, but there's several out there now that are open source. There's some APIs, and if you want to see something kind of cool, at least it blew my mind, look up on YouTube Kubernetes for children, I think it is, or something. But there's a really great video on what these container frameworks are about, and essentially it's the scalable technologies, lower level than Linux even, that allows like clouds to dynamically move all these services and processing across thousands of hardware or pieces of hardware. So they can do it with thousands, we can do it with 3 or 4. Okay, so just really cool technologies out there that need to be leveraged to improve our experience and the safety of the public. Just miscellaneous, kind of wrapping it up, miscellaneous stuff that's kind of being done out there. I didn't cover specific operation scenarios just because we have a wide range of experience probably on the call today. So if I speak about a specific operation that improves pedestrian operation intersection, I might lose somebody. But essentially, you know, like in central software side, using these modern protocols and technologies, instead of having to do some kind of custom integration for a controller or a different device, if that device supports JSON data and has some like descriptions of all the menu structure in its device and things, when it connects to the system, we can make a handshake where the system says, who are you? Should send me all your information. It sends basically the device sends the system its menu structure, and now that device could be automatically built into the system with very little or no interaction from a developer, right? So the ability to speed up process of integrating these things and to make it more usable for the agencies. Open APIs for sharing are out there using modern technologies. These ATSPMs, it's funny, it seems like kind of a legacy discovery of data management, but man, the analysis and like techniques and theories coming out of this stuff right now are crazy. People, agencies, traffic engineers, consultants are coming up with operation scenario, new graphs and charts to tell you how your system's operating that kind of blow my mind. Like it's pretty incredible what people are coming up with. Of course, connected vehicle support on the system side to push it up out into the cloud for anybody to subscribe to. And on the controller, again, more technology, just bringing web servers to controllers. Instead of having special software in your laptop you have to install and maintain separately, you can open a web browser, connect to the controller, and all of it's hosted there. So this may not seem like some dynamite innovation to you guys outside the industry or that are starting into it, but I'm telling you, this is big things in signal industry, and it's just speeding up. We need more innovation as time goes on. You can read some of these other ones if you have questions specifically. I do want to touch on onboard replay and analytics. So we talked about high resolution data. That does more than just analytics, right? So in a machine algorithm or software algorithm or software logic, you have a program. That program behaves based on rules set and then inputs coming in. So the high resolution data is recorded, and whatever's happening in the controller at that time for inputs is making the controller do something and output something, which means if we record that data, we can feed that recorded data back into the same computer logic program on the side while the controller is still running the intersection. And now we can replay what happened in the software at the intersection at that time. So if a technician or an engineer goes out to a cabinet and flash, something's wrong, instead of having to like spend hours troubleshooting, maybe it's a software bug, maybe it's not, maybe it's a programming issue, you can actually go back and replay it and see what happened in the software right before that failure. So now we know what's going on and we can isolate where we need to look first. Anyhow, and secure communication, secure interaction with all of our devices, end-to-end security is important for everybody in the network, not just the Ethernet switches. So I'm rounding up here around the corner. What's all this mean? All these technologies, you know, it enhances operations. Enhanced operations and better analytics also help improve safety. Prediction in the future could especially make significant improvements in safety in terms of operations and software. It's more efficient management, so we can do more with the same resources. We can interact with the system in a better way. The same system interface can maybe dynamically adapt to a director that wants to see some kind of dashboard versus a technician that needs to troubleshoot, you know, a detector hit list for his day's maintenance activities. And boosted security. Security, I know I've preached about a lot, but extremely important moving into the future, especially as we get into IoT, we start interacting with connected vehicles. We have got to improve our security and our infrastructure. So it's not just equipment and software and products. This new ideology is driving socially, like how we do business, how we interact with our equipment, how we interact with each other, how we think about the solutions provided, right? So if you look, it's not just traffic signals. Everything in marketing out there in the world is turning less from what this mop, all the special things about this mop. It's a 6-foot long handle. The mop is plastic, so it lasts longer, and it has a super sturdy mop end. I know nothing about mops, so I'd be horrible in QVC. But instead, we're moving, including our industry, is into solutions based. How does our solution affect you, right? So now this mop makes it easier because you can spray and mop without using a bucket and water. So it's a faster cleanup for on-the-go clean, right? That's the same with traffic signal industry. We're looking at solutions that change the lives of the users, including ourselves. And I think that's a big thing technology's done for us, is it's changed less from this is ABC, what it does, to this is the experience it can create. This is a solution, it can improve a life, things like that. And so bridging that gap between freeway and signals as well, as we migrate these technologies together and share more and have more devices integrated. Now, the example I used earlier, like a freeway system and a signal system, they start to bridge together. And with that, I'm not just managing a traffic signal network or a ramp meter and some detectors in the freeway. I'm managing an entire ecosystem of devices, right? And they're interacting with each other. So now if I have an incident in the freeway, I might change some DMS signs or VMS signs out in the road, change the variable speed limit sign, and maybe the system will recommend automatically that I need to go change a signal timing plan that's adjacent to the next exit ramp, because we're going to have a bunch of traffic getting off the freeway due to the incident ahead, right? So new scenarios to be done. Also, the people who suffer the most are often small agencies in terms of implementing newer technologies, just because of funding and limited resources. So new technologies make it easier to kind of expand their offerings and more affordable. And then I think just overall, we're trying to break that status quo, right? We're getting away from proprietary nature of, well, you bought a device in the field, so you have to buy the whole system. It's more about, here's a solution that maybe it's complete from one vendor, or if you want, you can pick and choose the solutions that are best from you. And the technology advancements and how the data is shared, how the devices interact with each other, how they're deployed, that is all what creates this kind of like blending of everything. So last but not least, what's it like to be a signal engineer these days? I think that, and maybe I'm misrepresenting this stereotype, but in the past, a traffic signal engineer to me was always somebody in a cubicle, maybe at a desk. I won't go as far as saying a pocket protector. I think we're beyond that, but sitting there managing reports, collecting data, maybe getting some information from the system, really interacting on a traffic signal operations basis. It's like I said before, when I used to be out in the field tuning a light rail network or something, I was more focused on what's my next, my whole focus actually was, how do I get that train moving without, with minimized delay to traffic signals? What's another PED feature I can implement? How do I reduce transition? It wasn't that, oh, we just installed a new controller with a new switch, and that switch, that communication switch still has its default password programmed, right? Admin. That wasn't on anybody's radar for years, or very little people. So I think the daily life of traffic engineer these days is, one is data management analysis. We're doing a lot more with data than we are standing on the street. There's still definitely need to be out there in the street, get that hands-on experience. But sometimes sitting in the office or even in the controller view out there in the field and getting those analytics can tell you weeks worth of information versus you just watching it for 5 minutes that day. So it helps us better manage our system. Also, troubleshooting, much easier and faster. Maybe we can even be prepared. The system can send a message to the technician that says, this is the potential problem. You need to make sure you take this equipment with you, right? Network configuration and monitoring. Most agencies have IT staff. Large agencies have very talented IT staff, but there's a lot of traffic engineers out there that are still managing their own networks. So that means that we have to have a knowledge, at least a base knowledge, so we know what's dangerous and what's not, of how to configure a network, how to monitor it, and when we need to ask for help. And then software technology stack maintenance. So all these new stacks, we're not working in Microsoft Windows anymore all the time. We're not working with SQL servers. So I remember I was in Professor Wang's class long ago, and I think it was statistics for transportation of some sort. And I thought, man, all these spreadsheets and data, am I really going to use this if I'm in an operations versus a theoretical kind of trade of traffic? And it turns out that he knew what was coming, because essentially data is what we work with as engineers every single day to figure out what's going on. And last is the research and implementation of new technologies. So as a traffic engineer, you have to have enough knowledge of general IT industry, security, cybersecurity. You have to have knowledge of operations in general. You have to understand networking, and you really have to understand, data and what you expect to get out of these systems to be able to go out and purchase new systems or identify or design them, right? So you can take people's word for what they can do, but you really need to be able to identify what the system's capable of, what it means in terms of maintenance, and what resources you might need to manage these new technologies. And so that means the skill set of a traffic engineer has really, I think, modernized to be data scientist, networking specialist, and also still have that core of traffic signal operations. And as you get more into management, and maybe even early on when you're presenting to a director or a manager, policy and politics, right? We really have to think about how our behavior, how our reporting, how our designs, how everything we do is affecting policy, as well as like the general public, the solution to the public, because we can have a bunch of politicians deciding where we invest our money and what we do next, or we can be educated in what we need to get the infrastructure up to speed, to improve safety, to improve operations, and we can start to lobby ourselves, right? Through whatever level, whatever means we have, but communicate. I guess the message is finding a way to break down all this complex information into something simple and high level that executes the point that we need funding to improve our infrastructure. So with that, I guess we can move on to some questions.
Thank you very much, Tom, for the informative and interesting talk. There are already some questions in the chat box. The first question actually has 3 different parts, so I will separate them. The first part is, how are connected vehicle technology deployments likely to be funded on both the vehicle and the infrastructure sides?
Yeah, that's a challenging one. So I'm part of a group right now at ATSA where we're actually trying to lobby Congress with some infographics and basic information to get better funding. Right now, it's not earmarked, right? It's up to agencies. They're using grants or private funding to manage this infrastructure and to upgrade the connected vehicle. Some auto manufacturers have committed. It's interesting. Some of the same auto manufacturers that were lobbying against DSRC and 4.5G, they were installing DSRC radios in vehicles, in high-end vehicles about 1.5 years ago. It is not a mandatory standard yet. That's policy that has to be implemented. And it's interesting to me because they make a big deal of it, but those radios, the technology that drives them is quite expensive, the R&D and software. But the radio itself, the hardware, is relatively inexpensive compared to, say, the price of a whole car. So I think that it's a difficult question to answer because there is no right answer right now. But there are standards organizations, there are committees that are lobbying Congress for funding, but also for policy changes going through like SAE, for example, that governs auto manufacturer standards. They're working on policies right now that dictate how connected vehicles will talk to the infrastructure, and also some of the basic operating principles in terms of what data they get back from the infrastructure and what they're going to do with that. So I guess the answer overall is we'll see, but there are gears in motion that are lobbying these things now, trying to, and standards that are creating standardized methods of implementing these things.
Thanks, Tom. So the second part is, do we expect V2I or V2X capabilities to be mandatory on future vehicles, or that at least some consumers will be willing to pay for them?
Yeah, sorry, I jumped a little ahead. I read ahead, I cheated a little bit. So I answered part of that maybe. I do expect it to be mandatory at some point. I would say a majority of new cars already have some kind of cellular technologies in them. Whether it supports V2X or not is unclear depending on the manufacturer. But I do expect that to happen, I think, within the next 5 years max. I mean, if you look at autonomous vehicles, people are working on cars that drive themselves back and forth across the nation with less accidents than would be normal for a human driver, right? Mm-hmm. So that is coming. It's moving very quickly. In terms of who pays for it, again, I believe, like, in terms of the biggest issue of who pays for it, you're going to pay for it in a new car at some point. You won't have a choice. But in terms of older cars that need to be upgraded, the consumer might have to pay for that. That's correct. And so there's actually, this is kind of a side note, but I think it's really interesting. There's I forget the name of them, but there's an association of auto repair shops. And I wish I could plug it because it's a really great organization. It's all about just auto repair shops that are licensed to work on cars, basically used cars or older cars, and even new cars, but not dealer network. They're trying to lobby also for open data and protocols, just like we do in traffic, because currently with all these new technologies in cars, including the autonomous vehicle and the connected vehicle information, the auto manufacturers are saying in the name of safety and security, we're not going to open that up to anybody. It won't be released, which means that moving forward, any new cars that go in to get serviced would have to go to a dealership for anything because they're all computerized, right? So it's kind of deaf to the auto shop, but also it takes power away from the user. So now it's not really, you own the car, but you can't choose who works on it, and you can't choose you can't read the data that it's generating, right? So it's almost like your cell phone. You own the cell phone, but you can't control where that data is going or who manipulates it. The other thing is, so like this auto manufacturer, the Auto Shop Association is looking at how they upgrade these older vehicles connecting into the CAN bus, right? So I think, Yinhai, I believe you guys have done some work with CAN bus, if I remember correctly. I can't remember, but there's some universities right now and also OEMs that are trying to work on, or this Auto Manufacturer Association are working to find devices that will plug into a used car and essentially create a connected vehicle out of that with an install. But again, it's not funded, and I would expect in the near term that if you want it when the technology becomes commercial, you'd be paying for it yourself. But these aren't really technologies that have made it past the commercial stage or past the pilot stage yet.
Yeah, so we are working with different parties for the connected vehicle technology. So these are still in progress. I think we'll share more once we get them done. The third part of the question, actually, part of that you have already answered, Tom, is about the infrastructure improvement funding. Will that be solely funded by the public agency, or is going to be more private involvement for the funding?
Yeah, I can add that a little bit. So I talked a little bit about how there is no defined funding mechanism. There are different groups lobbying Congress to establish policy around the mandates, if it's included in a car or not, and also around how to fund this. But then there's some agencies like the state of Georgia that they're pioneers in innovation, right? And in Utah as well. And they went out and they said, we're going to go out and buy thousands of radios, and we're going to make this a reality. Because if somebody doesn't do it, it's not going to happen. It's going to go a different route that we as traffic experts can't control, right? Because the private industry drives it. It would happen maybe faster, but we're going to lose control of what we know. So they're going out there and they're spending money. A lot of it was on DSRC, so that technology is being antiquated, or is being kind of sunsetted. But they're in a great position with their technologies to shift to V2X now, and they'll continue to do so. So it's like, I guess it's not a direct answer to the question, but there are agencies out there saying, look, we have the funding for R&D. We're going to be pioneers here. We might take the step in the wrong direction, but we'll back up and we'll keep moving forward wherever the industry goes. So to get on my soapbox real quick, I apologize if I'm taking long-winded, but it's up to us to help guide this, right? We know how a signal interacts with pedestrians. We know the various safety implications of shortening a yellow. Like, we know all these things about traffic that we can't expect an auto manufacturer, an outside party, to understand. And so that also means that we have to adapt and we have to think like them and work with them. We have to be accepting of these new technologies. We have to be accepting of new practices, because if we keep saying, you don't know how it works, we're going to use time-space diagrams and do whatever we do, then we're going to die as an industry internally. Anyhow, I'm preaching a little bit now. But
yeah, I guess these are all complicated to answer. So thanks a lot for your effort. Another question is about the state of the art traffic signal control methods. So my interpretation is you mentioned a lot of different things, including like machine learning for automation. So there's just a lot of new data coming, new methodology. How do you envision the future traffic control system?
yeah, so there's a reality that we can see in the near future, and then maybe what I envision long term. The reality in the near future is a state-of-the-art signal system would be a system that pulls this data in and does not require my eyeballs to look at it every day post-processing, but a live feed of this near real-time data, giving me a gauge of the health of my system. Not really health, maybe performance. It's hard to say, is your system healthy or not, right? But you can tell how it's performing compared to various days in the past, similar days. Maybe it compares to every Tuesday to Thursday the last 6 months. the ability to compare a snowstorm and how that affected the performance of my infrastructure versus versus what actually happens on a normal day where the streets are dry. Also, the system has the ability, let's say the snowstorm example again, to automatically detect a weather sensor, right? And the weather sensor tells it it's snowing. And now that system, based on various business rules that are established, changes signal timings, whether it's through a pre-programmed plan or using adaptive, and increases yellow times, or maybe that make people a little too worried. So maybe it increases all red time, and then it also changes the startup time for the signal timing pattern. So we're delaying the offsets a little bit, making our min greens a little longer. Also, the state-of-the-art signal system in terms of devices. In the field, we have modern operating systems. One of the problems of why we can't have a full-blown, computer that has a 4 gigahertz processor and 32 gigabytes of RAM is price. We have to have hardened systems out there in the field. And in my vision of state-of-the-art is that we have these modular controllers that we can easily upgrade engine boards for a cost-effective upgrade and enhance with more software or more capability without replacing the entire unit for $3,000. And then last state-of-the-art practices, I would say the ability to intertwine these different devices from third parties, not just signal controllers, but bring in all kinds of detection equipment, freeway management equipment, signal controller devices, pedestrian devices, bring them into one place where we can start to create new operation scenarios between them, sometimes autonomous, sometimes manual. But that's a tough question to ask right out of the box. But
yeah, so we have about 3 minutes left, Tom. We just have the last question in the chat box. So the question is, what would be the role of connected vehicles in the future? If that would be private use mainly, how do we make sure the safety if some users decline to update their systems?
That's a fantastic question. And I think that's where, in my opinion, that's where modern technologies come in, right? The ability to have these scalable technologies with over-the-air updates. If you look at IoT, that's really where connected vehicle needs to go. And IoT devices, the beauty of them is they're kind of like zero configuration integration. So of course you have to interact with them somehow, but the idea that you turn it on and it automatically configures itself based on some input parameters from you, it connects to the system. And then from that point on, it accepts over-the-air updates and things like that. If we take this into a political realm, I think that's where free Wi-Fi communications for all is important. Like maybe some programs that actually get people connected. So it's not going to directly update their car, but by having free Wi-Fi when they stop at their house, or if there's a Wi-Fi mesh network out there, it can dynamically push these over-the-air updates. In terms of hardware, that's just something that, just like the traffic signal industry, we'll have to continue to support the legacy hardware in the field until it becomes obsolete and disappears.
Thanks, Tom. So there are some more questions. Maybe we can just get one more answered. Most traffic signal research uses simulation to test the proposed new signal control methods. Do you have any easy solution to test new methods in real world?
Yeah, so there still is a place for simulation. That's a good point. But something I think that could make it even more powerful in this specific example is you could feed, instead of using data that's kind of like collected on a certain day or randomly generated, we could do two things. One, we could feed actual inputs from the field into the model now, so we can see, hardware in the loop from actual the field to see how it would be affecting the simulation at that time. Or we can use that data, so we can download months, years of data in some agencies, and feed that high resolution data into our algorithms, have the controller software in the loop. Like our controller software runs a VISM, so you can actually have every feature and functionality from transit priority to preemption to user logic. And you can see, using real input data from the field, what that would look like over time. So I don't think we have a direct replacement for seeing what happens if we put a new signal in or if we change the phasing, but the ability to integrate that into the system with a click of a button, pop something out that automatically models it in line with the actual signals running in the field, and then seeing how what outcome that provides.
Thank you, Tom. I think we're just at the end of the webinar. Some people are asking about if we have a recording. Yes, we do. Actually, this is a PacTrans webinar. We have a YouTube channel. Normally, we'll place our recorded webinars there. So it will take some time to process the recording and then post it. So once we get that done, we'll inform you. You could find the recorded webinars there, not only just this one, but also every previous recorded webinars. So with that, I really appreciate Tom for your time and your very interesting presentation today. And also thanks everyone for joining our webinar. And I hope you keep attention to other PacTrans activities and join us. Thank you very much and have a nice day, everybody.
Thank you.
Goodbye.